week's seminar.
This meeting is being recorded.
So just so you know, Boone, this meeting is being recorded. Okay.
Perfect.
All right. So our seminar speaker this week is Geoffrey Beausoleil from Idaho National Lab. He goes by Boone. And a few words about him. Geoffrey, or Boone, he's actually a staff scientist within the Fuel Design and Development Department at Idaho National Lab. And he's involved in several projects, which include leading the AFSC, the Advanced Fuel Cladding Fast Irradiation Experiment, leading and contributing to multiple LDRDs. For the students who don't know, those are large research programs within the national labs. And he also serves as the technical lead for testing and characterization in advanced manufacturing and materials technologies. His involvement is primarily in the development of accelerated methods of irradiation experiments and post-irradiation characterization. He's had experience in the past with refueling and plant overhaul of aircraft carriers and submarines in the Naval Nuclear Propulsion Program. He has also performed research on ceramic membranes for gas separation and fuel cells, as well as development of dilute magnetics, semiconductor nanomaterials for both magnetic memory applications and cancer therapies. So definitely a materials guy. And today he's going to talk to us about fuels and current irradiation campaigns that are ongoing at Idaho National Lab. So with no further ado, Boone, the mic is yours.
All right. Thank you guys very much. Thank you for the wonderful introduction. Like Jamel said, my name is Boone Beausoleil, and I'm at Idaho National Lab. So I think to start off with, at risk of this is going to be the Cliff Notes summary version, but we made this really cool video that basically summarizes what I'm about to talk about, and I'd be remiss if I didn't share it. Although it just dawned on me, I don't know if the audio comes through on this very well, so someone signal me if you can't hear this at all.
As energy needs increase, we need to produce more electricity with fewer carbon emissions. The next generation of small nuclear reactors promises abundant clean energy at a low cost to consumers. Advanced compact reactors can also be quickly deployed to remote locations or areas experiencing a disaster. Reducing the testing period and costs for fuel systems is critical to develop these reactors. Idaho National Laboratory is taking on this challenge with its Transient Reactor Test Facility, or TREAT, and the Advanced Test Reactor, or ATR. INL researchers have developed 2 new experimental capsules to streamline the testing process for fuels by reducing the size of the experiment while maintaining prototypic conditions. The FAST experimental capsule is used in ATR, which helps researchers perform irradiation experiments over 4 times faster than traditional tests. This can reduce a 12-year experiment to 3 years or less, saving up to $3 million in testing costs per experiment. Experiments can then be tested in TREAT using the Thor capsule, which allows us to test accident conditions and ensure fuel safety in every scenario. These 2 tests at INL ensure that the advanced low-enrichment reactors currently being developed can operate safely and economically, providing clean energy wherever it is needed.
All right. So that is essentially what I'm here to talk to you guys today about, is some of the irradiation testing that we do for fuels campaigns here at INL. So the discussion topics that I want to try to cover today include, 1, why nuclear? And I realize that this is a nuclear engineering department, but I think it's an important question to revisit every now and then to make sure that, there's a variety of reasons and motivations that we all have for being here. And these are some of mine. And then the next question, what is a radiation field testing at ATR, and what are some of the barriers that we've had from conventional field testing? What can be done to make it faster? And there's an intentional reason for the capitalization of that acronym that we'll get to in a little bit. And then also first look at PIE, or basically what are the results told us so far, and what have we seen from this, and how is this working? So to start off with, the first question is why nuclear? And for me, this is primarily a humanitarian reason. I mean, one, it's fascinating, sure, but primarily it's a humanitarian reason, right? By 2040, it's expected that the world's population will exceed 9 billion people, and that the energy demand for those 9 billion people will increase by over 93%. And on the right-hand side here, right, you can see that this is our Human Development Index, or basically a standard of living comparison, or index for the standard of living versus energy consumption. And in order to have what we consider in the Western world to be an adequate standard of living, you need to be consuming at least 3,000 kilowatt hours per year per capita. And so up here, right, we see all these Western developed nations. And on the other side here, we have a lot of developing nations, right? And there's nations that are industrializing and have every right to do so. And the easiest path to industrialization is the same way that we all did it, and that's through burning a bunch of coal and oil. But in hindsight, we know that's wrong. Well, we know it's not ideal. And so I think there's an opportunity we have to be able to help provide a better way to industrialize and a better way to achieve a high standard of living and quality of life without compromising the already delicate environment that we currently live in. In addition to that, there's just a bunch of other good reasons. Educational opportunities, gender equality. As you can see, I'm sure you've probably read through some of this a little bit, but there's some huge issues, huge human issues that are highly dependent upon reliable access to electricity and dependable access to electricity. And at least for me, and I know a lot of other people, that's something that nuclear can provide, right? Which then begs the question, why do we need new fuels? Well, to start off with, there's a series of reactors, right? Most people know are referred to as Generation 4 reactors. And these are kind of generally defined as these 6 type of reactor platforms. And for the purpose of this talk, I'm going to weigh heavily upon the sodium fast reactor, and generally has the similar, some of the same applications to a lead fast reactor. But what is wrong with LWRs? Like, why do we need a Generation 4 reactor? Well, from an environmental standpoint, and this also kind of answers this third question about other energy sources, the name of the game is carbon reduction, right? So we can look at the carbon output per kilowatt hour produced by a given source, and as we'd expect, there are a bunch of carbon or fossil fuels, biomasses, and things like that, things that are carbon heavy, are going to have a high carbon output. Now we start comparing those to other energy sources, and this is a cradle to grave, right? So this is raw resources out of the ground to disposition in the ground. You can look at a variety of renewable sources, you can look at LWRs, and they're in this range, right? So we're 15, 20, something along those lines. And that's obviously very good, right? It's 4 times better than this side of the spectrum. It gets even better, right? If we can go to like a gas-cooled reactor, we can go to hydroelectric, we get in the vicinity of 7. But this number right here is huge, right? This is roughly 1 gram of carbon per kilowatt hour produced, and that's for a fast breeder reactor, right? So something like EBR2, or the experimental breeder reactor, eventually IFR, the integral fast reactor, possibly any of the other types of advanced reactors being put out there right now, almost fall into this category. And there's a variety of reasons, but the big takeaway, right, is this is an order of magnitude better in carbon reduction than any of these renewables or LWRs. One of the dilemmas to that, of course, is getting to a reliable, safe, and qualified fuel system. So what is the challenge of developing new fuels? About 15 years ago, this paper was put out by a variety of people who spent most of their career studying these advanced fuels through the EBR2 legacy, as well as some other fuel development opportunities. And they put together this kind of general timeline and paradigm for conventional fuel qualification. Right? So you can kind of start somewhere in this circle, and work your way around through these different stages and integrate back and forth with modeling and simulation and so forth. And for the most part, this takes, even using a lot of the historical data and precedents that we've already established in past field testing, this takes on the order of 20 to 25 years, which is a very long time, right? So it's, 2022 right now, and we're looking at 2040 is 18 years away before we kind of reach this huge threshold. And there's a lot of reports out there that indicate we have major consequences if we don't start curbing carbon emissions at that point. And 2050 is kind of this, deadline before we really start losing things like ice caps and we start experiencing a much more rapid, semi-mass extinction catastrophe in our climate. And those things aren't immediately repairable either. It's not like we get to 2050, dump a bunch of nuclear plants, and here we go. Like, we need this decade in order to make meaningful progress into stopping these things from happening. Whoops. All right. So there's an urgent need to develop a new paradigm and deviate from this historical one. So recently, there's this methodology or kind of accelerated fuel qualification, or AFQ kind of approach has been taken between a variety of different vendors. And so we worked on, so this paper was authored by various people from both INL, Oak Ridge National Lab, General Atomics, and a couple of other companies. In general, there's a working group through DOE on this and how we can start developing accelerated methods to move fuel qualification at a faster rate. And this is a high-level summary of what that looks like, right? So you start off in the first little bit of time here with some basic physics, right? So we understand radiation effects, we understand thermodynamics, we understand how most of the usable elements on the periodic table behave. And we've got a really robust, material science framework for understanding how some of these things should work. Of course, it's not always that simple, but it gives us the first go, right? And you can kind of put this together in this first year or so time frame and feed that into the phase 2, which is going to be, starting to look at separate effects testing through different material systems and fuel systems. You can look at basic performance analysis and start putting together some, very basic integral thermal mechanical behaviors or thermal mechanical models. You start partnering this with something like MOOSE, which is a fuel performance, physics-based, ideally physics-based material performance analysis tool developed at INL to integrate with a lot of the experimental efforts that we're doing. And as you start doing this, you start identifying like fuel specifications, you start identifying, reactor performance margins and such, and you start feeding that into this third stage where you can start doing more integral fuel testing and understanding the combined effects of all of these different physics and so forth. And if you do this right, you identify a variety of different performance spaces that you can validate models against. You can start gaining credibility into projecting into, untested space. And you can start putting together, ideally, a licensing basis, right? So if we add all this up, our phase 1, 2, 3 stage to get to a licensing basis, to start looking at, LTAs and getting this out there is on the order of, 7 to 10, possibly even 12 years, that kind of a time frame. And that's something that is, in context to all the problems we're trying to help, solve, much more palatable than 20 or 25 years as a minimum. So some of the tools that we use in doing this within the DOE complex basically come down to three primary reactors. The first one is the high flux isotope reactor at Oak Ridge National Lab. And there's a lot of really cool things that HYFER does. It's a fantastic material testing reactor. It has some awesome beamlines for characterization. It even has some really awesome fuel tests. So Chris Petrie, one of my colleagues at Oak Ridge, leads the mini fuel test. It does some really awesome special effects. And if you're interested in knowing more about that, I'm going to leave it there because it's also not my reactor and it's not where I spend most of my time. But very powerful tool. The second reactor in our complex is TREAT. It's the transient test reactor. It was temporarily put offline in the 1990s and re-brought back up and restarted in 2018. And for those of you who don't know, I guess essentially transient, this is basically an off-normal excursion or power excursion or off normal, circumstance that you want to test fuel safety in, right? So talking like a LOCA, an RIA, something that might be a very high energy deposition experience for a fuel system. And you need to understand what that looks like. And so TREAT is very good at being able to do shaped power transients, things on the order of nanoseconds, milliseconds, with huge amounts of power and a variety of different thermohydraulic environments. And so there's some really cool tests going on with that. But again, I'm going to transition to ATR because that's where I do the vast majority of my testing. But these two are very, very similar, as that video showed, right? So we're currently working at making sure that these two things are working in tandem to understand all of the fuel safety characteristics that we need to know. I guess real quick, as a quick side, and I'm going to propagate the urban legend because I like to believe it's true, but TREAT is a graphite moderated reactor. And so inside of here, there's a whole bunch of graphite blocks used to help control the reactor. And the legend is that when they decommissioned the Fermi reactor in University of Chicago, they moved the graphite from the Fermi pile to Idaho and used that to build the TREAT core. And so we like to claim that TREAT is the longest continuously operated man-made reactor in the world by virtue of the fact that the graphite is harvested from the Fermi pile. So the last reactor is ATR, the Advanced Test Reactor. It's a very unique reactor. It has a variety of very interesting characteristics that are better detailed on this page. So to start off with, rather than having reactor rod or fuel rods or anything of that sort, it's got this very cool plate-built serpentine fuel system. So this yellow band here is the fuel structure for this reactor. And it's very interesting because it creates a variety of unique testing positions, of which there's over 60 different test positions that you can test in. The most notable of which are probably these flux traps, right? So we've got our cardinal directions from the compass. You have a north, east, south, and west, and northwest, northeast, and so forth lobes. And each of these flux traps supports some very exciting experiments. It hosted the AGR Advanced Gas Reactor TRISO 567 experiments. It hosts the accident tolerant fuel 2 experiments. It hosts a variety of naval experiments and some other type of experiments like that. It's very good for loop testing, very high flux positions. In addition to that, you have some in-core positions like these A positions in these little green circles here. They're kind of hard to see, but right next to the center flux trap and the corner lobe, you've got these positions. And then surrounding your cardinal positions or cardinal directions, you've got these orange squares, which are circles, and those are our B positions. And so these are basically our center core reactor positions. And they typically have a flux on the order of 10 to the 13 fast, 10 to the 14 thermal. You can have in the flux traps a peak flux of 10 to the 14 fast, 10 to the 15 thermal. After that, you've got the control or reflector drums surrounding it, and then these big green circles on the outside is the periphery, and these are the I positions, and those typically run 10 to the 12 to 10 to the 13 fast and thermal, respectively. One thing about this is that it is a rather cold reactor. The coolant temperatures range between 50 and 55 C. Sometimes if you have a very hot experiment, the outlet might be on the order of around 60 C. Or 70 C at the very most, but generally a rather cool experimental environment, which is problematic for some testing because most of the actual power producing reactors we want have coolant outlet temperatures on the order of 400 degrees to 800 degrees, just depending on the type that we're looking at. So it requires a little bit of engineering. But before I get into that, so I kind of want to touch base real quick and make sure some of the things I'm going to touch on are understood. So for metallic fuel, which is or an alloy fuel that we use in the past for EBR2 and most sodium fast reactors, one of the big things that we talk about is called smear density. And so smear density is basically the ratio, the starting ratio of the cross-sectional area of my fuel divided by the cross-sectional area of the inside of my cladding. So basically, R squared of the fuel over R squared of the inside of the cladding. And after a number of decades of testing, the kind of magic number that people have fallen to for most of this is around 75%. And so that's kind of been the standard, and that's what the final driver fuel for EBR2 was at. And some of the reasons for that is that it maximizes the opportunity for swelling. So essentially, metal fuel becomes very, very plastic. It starts generating a lot of fission gas. It creates, you get defects. Defects become pores. Pores get filled with gas, and gas starts swelling at high temperature. And it just becomes very, for all intents and purposes, soft and spongy in places. And so we have to create space for that to swell to. Otherwise, you end up with excessive strain on the cladding from solid swelling and fission products. And in general, a higher smear density means lower available swelling, right? So initial first stages of fuel for a lot of fast reactors had smear densities of 90–95%, and they had burnup limits of around 1 to 2 atom percent because of cladding rupture. 75% seemed to be the magic number because it allowed the maximization of a pore structure to form and then release of fission gas into an open plenum above it. Now, prior to that, you'll see this blue circle here is bond sodium. Since this doesn't start in mechanical contact with the cladding, you have to do something to ensure adequate heat transfer from the fuel to the coolant. And so to do that, the way they do that is to fill this with sodium and melt it down. And so you end up with a thermal bond from the fuel to the cladding through the sodium. And sodium melts at around 102, 103 degrees C. And so once this fuel starts heating up, it's on the order of 500 or 600 degrees C. That sodium melts is more than melted and provides a very good connection between this by virtue of it being liquid. As the fuel swells, it does displace the sodium. The sodium does a couple of things. It backlogs some of the pores, and so you have sodium logging in that pore structure, and you have sodium displacement to the top of the fuel into the plenum space above it. And so all those things will be important in just a moment. But I think that for the most part covers some of the things that you'll need to know to kind of understand the novel fuel tests that we're going to be looking at. So to start off with, we'll look at past AFC irradiation tests. So AFC is the Advanced Fuels Campaign. It started in the mid-late 2000s to explore a variety of advanced reactor fuels in support of the Generation 4 movement. And so the irradiation tests done on this at INL were primarily focused on exploring alloy fuel solutions to the problems previously experienced in EBR2. One of the problems with that, though, is that EBR2 and fast reactors have a fast spectrum. ATR is predominantly a thermal spectrum on the order of 10-to-1 fast or thermal to fast neutrons. And so in order to make sure that you have prototypic fuel behavior, you needed to correct for that. So to start off with, we'll look at an average power profile for the fuel. And so the blue curve on here is a rough estimate, basically a simplified estimate for what the power average, local to average power would be for a fuel rodlet as a function of radius. And if I put that same rodlet into ATR without any assistance, I end up with this red curve. So I end up with a high power peaking at the periphery and a high power depression in the center of the fuel, by virtue of the fact that the thermal neutrons don't make it there. And so this gives you a really unprototypic power or burnup profile, which has a significant impact upon a lot of the fuel performance metrics that you're trying to look at. So to solve that, we created this AFC basket. And this blue ring at the top here is a cadmium shroud. Cadmium has a very high absorption cross-section for thermal and low epithermal neutrons. And so it allows you to basically harden the spectrum by chopping off everything that you don't want to have. It's not entirely prototypic of a fast spectrum reactor, but it's about as close as we can really get in ATR. And the effect of that is this black curve. And so it gives us a power profile that's much flatter and a little bit more prototypic, and allows us to have pretty typical fission behavior. So inside of this is the capsule. Now, if you remember, I mentioned that coolant temperatures in ATR are on the order of 50 degrees C. Coolant temperatures in an SFR might be on the order of 500 degrees C. So to achieve those temperatures, you have the stainless steel capsule on the outside here. And then on the inside, you have your cladding and rodlet. So this dark gray or black is the cladding, the yellow is my fuel, and that white ring between that is a gas gap. And so if you've done heat transfer problems before, or thermal hydraulics is your specialty, you'll probably know that, you would know this, but for everybody else, gas is a really poor thermal conductivity medium. And so if I need to raise the temperature on something inside this capsule, in spite of the cold temperature here, I'm going to use a gas gap and fill it with something like a helium-argon blend. And that allows me to achieve prototypic temperatures inside while maintaining relatively cool coolant temperatures on the outside. Now this has some problems and challenges. One, I will say this has been incredibly successful for the most part in being able to do an awful lot of very valuable and very good research at a variety of fuel designs, but that's not without problems. One of those problems is that we have a fabrication tolerance when we machine these of about 1,000th of an inch, which is roughly 25 microns. And the gas gap that I'm talking about in here is only 50 microns wide. And so it's not unreasonable to it's very believable to see how a plus or minus 25 micron tolerance on a 50 micron object gives you a 0 to 100 micron range, right? And same thing with straightness. So these fabrication variations and eccentricities can be catastrophic to an experiment, as you can see on the bottom of the screen. One of the AFC experiments that was in the reactor for 4 to 5 years came out, went into PIE, was sectioned out for metallography, and mounted, and we observed that half the fuel was melted. And so you can see on the right-hand side here, this excessive porosity. You can see the ingress of the fuel into the cladding. And it's incredibly problematic because essentially it becomes a failed experiment. And the reason for that is because of these variations. And essentially the variation in that is that if that gap becomes larger, like 100 microns, then the heat transfer through that gap is significantly dampened and the temperature of that local region becomes significantly increased. Or the reverse could be true, that my experiment could also just be significantly colder by virtue of the gap being smaller. So we revised this into what we call a FAST approach to experimentation. And there's a variety of challenges, but FAST stands for Fission Accelerated Steady State Testing. And so it's an accelerated platform that hopes to improve the time frame for performing field tests and qualifications, looking at improving experiment reliability, and then also providing a broader opportunity for experiment design parameters. And the way FAST works is by taking the same capsule that we started with out here, that's this gray circle here, taking everything inside of it and scaling it down by some factor of alpha. And in this case, 1/2, right? So you can take the cladding and the fuel and scale it down to 1/2 the original size. And then to maintain that original gas gap, we'll simply insert a second concentric capsule inside of it. To maintain thermal bond between the capsule and the fuel, going back to our trusty friend sodium and filling this with molten sodium, and the total experiment ends up looking like one of these two. So the A right here on the left side is a small I position experiment, and so this goes into one of those peripheral positions on the reactor, and this narrower one, B, is an outer A position. And so you have this capsule, which is the standard AFC capsule. You have this inner capsule inside of it, and it's kind of hard. Obviously, it's very small distances, so you can't really see the gas gap in this. But at the end of the day, you end up with a small little rodlet that fits inside of here and is immersed in sodium. This capsule here was the ATF capsule, or accident tolerant fuel capsule. We put in a second capsule inside of it, and then we stacked up two rodlets on top of each other. And this one right here, the ATF modified capsules, become kind of our workhorse for most of the fuel testing that we'll talk about. Now the two, so again, here's the kind of cross section again. You've got a fuel, sodium, and it kind of roughly looks about like that. Now, the first thing to talk about is the increased burnup rate. So if we assume a given heat power density of Q naught is basically going to be the linear heat rate that we have for fuel, which is a kind of a standard notation we use for describing the heat generation of the fuel, and we divide it by its area, we end up with that power density. So if we scale the radius of that fuel from here to here by some factor alpha, and we maintain an equivalent heat generation rate or linear heat generation rate, then the power density essentially increases by 1 over the square of that scaling factor. And so in the case that alpha is 1/2, the new power density of our reduced scale fuel becomes 4 times the power density of the original fuel. And the time that it takes us to get to some sort of target burnup is inversely proportional to the power density of the fuel. And so therefore the time to that target burnup is roughly 1/4 of that original time. This does create some additional effects to work through, but as we'll show in some of the initial PIE that we have, most of the fuel behavior is appearing to be fairly prototypic, and as we expect. But yeah, we'll hold off on there. The next objective, right, is thermal stability or experiment reliability. So remember here we have this melted fuel side that was caused by fabrication eccentricity, and now that eccentricity or variation is well within the tolerance and past inspections. But again, you can only machine things down so fine, and machining to a 25 micron tolerance is a very difficult thing to do. But we improve this by distancing the portion of the experiment that we care the most about from the portion of the experiment that has the highest sensitivity to those tolerances, right? And so by taking the experiment, the fuel and the cladding, and pushing that farther away from this gas gap, you become less sensitive to the variations within that gas gap. In addition, the use of a high thermal conductivity material around it, like sodium, allows you to also neutralize or kind of normalize any of the local variations within this capsule to the generic or kind of nominal dimensions of that capsule, right? So heat transfer through the sodium is very high. Sodium's got a thermal conductivity on the order of 60, 70 watts per meter Kelvin, whereas the steels are on the order of 20. And so just being able to quickly move heat away from here to a variety of directions and not just in a radial direction has some powerful benefits. So these two things are seen in a couple of different ways. One is in capsule offset. So this inner capsule for the fast test is this bottom side of these two thermal maps. And the cladding, which is roughly the same as that inner capsule, is for a standard test is on the top side here. So I've got a standard AFC experiment on the top, a fast experiment on the bottom. And what we did is intentionally just offset the position of the cladding or inner capsule by 1 mil or 25 microns, right? So I have a larger gap here by a 50% larger gap here and a 50% smaller gap on this side. And so I end up with a hot side and a cold side. And the temperature differences on this are pretty significant. So if I look at like a 300 watt per centimeter standard test, I end up with a temperature difference of about 120 degrees from one side of my fuel to the other, which is a very significant temperature gradient to have. And over the course of a long experiment that's taking 5 or 6 years, it's not something that you really want to see because it's going to cause some very significant variations in your fuel performance. Now, the half diameter size at 300 watts per centimeter, you can move this over, and I end up with a total temperature difference from my hot side to my cold side of about 20 degrees. I do end up with a slightly cooler experiment, and part of that is due to moving the relative colder side and the sodium being able to pull more heat away from this. So the net temperature of my experiment goes down a little bit, but the general impact to the experiment in terms of a homogeneous behavior is pretty minimalized. Now, additionally, and this is just an offsets caused by the inner capsule. The other question is what happens if I have a rodlet that is either rotated or tilted or whatnot and not centered within, isn't an axisymmetric condition. And so we tested this in part because we actually had some of the rodlets that were fabricated fell into this category where some of the tops tilted over from the rodlet holders, the bottoms snapped out of the rodlet holders, and the net difference on all of these was on the order of 10 to 15 degrees from the original experiment. And again, part of it is because having such a large sodium bath around this, it was so beneficial in being able to remove heat in a variety of directions that it dampened any of the radial offsets that we would normally have experienced if it was something like a conventional test. I'm going to come back to the neutronics, right? So part of the acceleration, we talked about the general idea of it. And that was kind of the scoping hand calculation used to kind of justify, going forward and testing this in more detail. But the numbers really speak well for themselves when you actually put it into an actual experiment analysis. And so we did some comparisons between, a full diameter, small B position test. And so this is a small B position, center to the core, center to the reactor. It has a cadmium shroud, so that it has, primarily the fast spectrum. But it's important to note that the fast spectrum flux in the center of the reactor at 10 to the 13 neutrons per centimeter squared is roughly the same as the thermal flux on these small I positions at 10 to the 13 per centimeter squared. So in terms of total flux, these experiments are roughly the same. I should also note the small I positions do not have a cadmium shroud. But the time to reach 30 atom percent for these metal fuel experiments is pretty significant for a full-size diameter pin. It takes us roughly 12 years on a normal ATR schedule to get there. Doing a half diameter and 1/3 diameter pin takes us about 1.5 to 2.5 years to get to that same burnup level. And while there may be unprototypic conditions that you experience, the benefit of being able to do PIE 10 years earlier and being able to think about that and iterate to the next level of experiments or even make qualitative comparisons to known standards is an incredibly powerful tool for moving the time, reducing the time frame of a qualification or fuel R&D program. Additionally, by moving the diameter, by making the fuel smaller, we can take away the cadmium shroud and still end up with a relatively prototypic power profile. We did some scoping calculations for UO2 as well and had a similar experience. We have a very prototypic power profile, both the beginning and end of the life, and the acceleration for just even a mild enrichment increase for a 1/2 diameter pin is pretty significant to go from 12 cycles to 5 cycles in ATR. So that's roughly 3 years to about 1.25, 1.5 years. So what are the AFC FAST objectives, right? So we put together a big test plan, a bunch of experiments, and the objective of these is primarily to look at ways to increase the burnup threshold of metal fuel. So in the EBR2 days, metal fuel was typically limited to somewhere in the order of 10 to 15% burnup, and that was due to some cladding strain limitations. And the cladding used in these fuels is primarily HT9, which is a ferritic martensitic or nickel-free stainless steel. It's predominantly iron, and that's problematic for a variety of reasons. One of those is that iron and uranium have a relatively low temperature eutectic of around 740 degrees C. And if you've got a ternary fuel, so a UPU zirconium fuel, iron and plutonium have a eutectic of around 490 degrees C. And so the risks of the fuel interacting directly with the cladding and causing problems is fairly high, especially in a ternary setup. Additionally, one of the primary solid fission products that we get in fast reactor fuel, alloy fuel, is neodymium and cerium and a variety of other smaller concentration lanthanides. But it's problematic because lanthanides have a tendency of migrating to the fuel cladding interface and then having a fuel cladding in chemical interaction, or FCCI. And so you can see that in some of these micrographs and these EDS plots where you have fairly high neodymium and cerium concentration on the interface of the fuel. And it's problematic because it forms intermetallics with the iron. And when you're strained, the strain on your cladding is dictated in part by the thickness, the viable thickness of your cladding. Cladding wastage is a huge problem. And so you have to start accounting for that within your models and within within the limits of the fuel. And so if you can limit that and get rid of these FCCI risks, you can feasibly increase the overall burnup limit of the fuel to something in the order of 20 to 30 atom percent. So some of these solutions, there's been a lot of work at trying to find ways to arrest lanthanide migration by the use of additives and varying other elements during the alloying process. And so if you have something that tends to form intermetallics with the lanthanides inside of the fuel, then they can't ever make it to the cladding and therefore not cause problems. In addition, you can have liners, some sort of, a thin, film type material or something mechanically pressed into the inside or coating inside of the cladding to eliminate the interaction with the iron-based cladding. Additionally, there's the idea of using annular fuel designs. And so rather than having my fuel swell outward into an open space around it, you create a hollow annulus in the center of it and allow it to swell inward. And what that means is you can start with your fuel in mechanical contact with the cladding. And if that's the case, you can get rid of the sodium. Getting rid of the sodium has a variety of benefits. One of it is, there are some safety benefits with it. It has, there's some void coefficient problems with sodium that are problematic for some safety reasons. Two, sodium creates a hazardous waste. You have mixed waste disposition pathways for your fuel. But three, and this is perhaps most important to this concept, is that sodium is seen, and this is still a little bit debated, but sodium is seen as a pathway for lanthanide migration, or at least helps assist in that lanthanide migration. So if we can get rid of that, there may be some benefits to that as well. So the test matrix that we have for the first round of AFC fast experiments is right here. There's a lot of different fuel tests. They include helium bonded annular fuel, so sodium-free design. It includes additives with palladium, antimony, and tin. And then it includes zirconium liners on the inside of the cladding. All the cladding for these are HT9 cladding. And each capsule in the small I position, which is, again, this capsule right here, includes both a novel experiment and a control experiment. And so that control experiment is just a solid 75% smear density U10 zirconium, that's 10 weight percent, zirconium, roughly 22 atom percent, fuel in HT9. And so that's something that represents about 9,000 different fuel pins we've done work on from the EBR2 legacy. So something we have a very good handle on the operation of, but it gives us something to compare these novel designs, qualitatively speaking, back to what we have a very good history on. And so these range for a variety of burnups, some low burnup fuels, which are the first ones that we've taken out of the reactor, which is what we have PIE on, as well as a variety of fuel rodlets all the way to much higher burnups. So I think I still have a little bit of time for some of the PIE questions, or topics at least. It's running a little bit over, and I apologize. So the first completed irradiation test, like I said, in orange are these first four, these fast tests for an annular design, as well as just a couple of controls at low burnup. Additionally, there's another program that was interested in looking at some U-moly at some moderate temperatures. And so these are some U-moly fuel that we're doing some burnup on, or PIE on as well. But the interesting thing is all of these were irradiated for one cycle, and we had burnups on some of these in the order of up to 7% for some of these U-moly tests, right around 4 to 5% for the zirconium tests, and some burnup. So the acceleration basis for this was pretty significant in terms of comparison to conventional testing. All of these fuel pins have been brought to HFEF. HFEF is our hot cell. It stands for the Hot Fuels Examination Facility. I will argue that it is the world's premier or best hot cell for fuel testing and fuel characterization. It has a very large hot cell. There's kind of a cartoon schematic of it right here. Here's a view looking down across the hot cell. It's about 70 feet by 30 feet wide. It has a variety of different cranes. There's workstations through a bunch of different windows along the walls here. Each one of those workstations has two sets of manipulator arms, which are these big, long pneumatic robot arms that allow you to handle the materials and control things. And then 4-foot thick windows for obviously irradiation protection. Downstairs is the NRAD facility. It's a radiography facility built off of a trigger reactor that we use for radiography. So there's a couple of beam lines that we can do characterization on there. There's some very interesting equipment. The FAX furnace, it's an accident testing furnace used by the TRISO program. There's the we have gas collection, so we can puncture rodlets and collect and assay the fission gas inside of those rodlets. Met boxes for slicing and mounting fuel specimens for advanced microscopy and other characterization. To kind of real quickly breeze through this, we've initiated the first stages of PIE. We were able to successfully disassemble and remove the rodlets from the capsules. So here's FAST 007. We have a special heater to be able to melt the sodium and withdraw the sodium out of that capsule. We spray it off with moist argon and you end up with a clean rodlet. Those clean rodlets get fitted into a rodlet holder that's fitted to be able to help support both radiography and precision gamma scanning. So here's some of the first look radiography of these experiments. So we can see FAST7, which is an annular design. Normally, if the annulus hasn't closed, you would see a faint line in the middle, and that can be confirmed with epithermal radiography as well. And we did, and we found that the annulus fully closed, which was exciting. These two tests, you can see there's a little bit of slumping, which is quite interesting. They weren't fully smeared, which you normally would expect at around 2 to 3% burn up, but they also were irradiated at a much cooler temperature than we originally planned, and there's some programmatic reasons for that. But so that also has the idea that if it's entirely within an alpha region, there's some reduced alpha swelling, or reduced swelling from that. And so there's some really interesting things we're going to have to look at through advanced microscopy. Gamma scanning looks generally somewhat what we'd expect. There's three things we typically look for in this: it's cesium, rubidium, and cobalt. The cobalt gives us good indications as to stainless steel components, like the ends of our cladding pieces. The rubidium gives us a good indication of our general burnup characteristics, and all of this looks pretty normal and what we'd expect. The cesium behavior is a very good indication to the sodium behavior, again, because the cesium will tend to melt and mix into with the sodium. And we get a couple of interesting things. We get these, normally would expect these peaks because the sodium gets displaced to the top, and so you have an increased peak of cesium outside of the rodlets, which we see for these sodium bonded experiments. The interesting thing is this FAST 007, it was the annular helium bonded experiment in which there's no sodium for that cesium to go into. Cesium has a tendency of migrating to cold spots, and so we end up with some axial gradients that the cesium would go to since it's not mixed with the sodium at the top and the bottom of the pin. In addition, any cesium that was jettisoned up here would, be able to start vaporizing and start plating out along the cold walls of the cladding since it's not trapped within the sodium. And so this will be an interesting thing to be able to break open destructively and start identifying some of those behaviors. I'm going to go ahead and jump past this for the interest of time, but real quickly, in parallel to all this, we're doing an excessive amount of modeling using the Moose and Bison platform and comparing it to a variety of EBR2 and FFTF models. And one of those goals is to be able to look at the full length, 40+ inch EBR2 rods and be able to identify, specific locations that we've characterized with compatible or comparable fast tests. This is a look at how you can identify, use small testing to characterize a much larger, more prototypic geometry. So what does the future of FAST look like? Well, like I said, there's advanced PIE, so we're going to be doing gas collection, destructive testing through microscopy, metallography. There's additional irradiations that we're looking at doing. We've got higher burnup rodlets. The rest of that test matrix is going back into the reactor this spring. And then again, this next fall for an additional cycles. There's other advanced fuels being looked at. So there's a variety of high thermal conductivity UO2 designs that are being irradiated. We're looking at uranium carbide fuels for high temperature gas cooled reactors. We're starting to go through some of the design efforts for some MOX fuel. So it's a mixed oxide fuel, a uranium plutonium oxide for some LWR applications, as well as just additional alloy fuels for other fast reactors, such as the versatile test reactor or VTR. The design is also kind of taken on an evolution. So on the right-hand side here is a schematic of the ESA capsule, which is taking the FAST methodology. It includes some passive instrumentation like flux wires and melt wires in the tops and bottoms of the capsules. And same kind of concept, it allows you to hold up to 2 different, reduced scale rodlets inside of a larger sodium bath and in a double capsule environment. So with that, go to ask if there's any questions. And thank you very much for your time. And sorry for kind of racing through the PIE part. So
thank you very much, Boone, for this this talk and this opportunity actually to learn about fast reactor, which seems to become a flagship reactor, test reactor for Idaho National Lab after ATR. So if there's any questions, maybe we'll start with people who have questions in the audience.
Does anyone have questions? All right, so no questions in the audience.
So if not, I have a little question in terms of the data that you presented there, the temperatures that you presented there. How are they? Were there measured temperatures or are they calculated temperatures? Is there a way to monitor the temperature in your capsules?
So the first generation of these experiments do not include any instrumentation. So all of these temperatures are calculated based off of the, so the initial ones were the, proposed, heat rates. Everything that we have in documentation for post to couple with the post-irradiation examination or PIE is calculated through the ASRUN power histories and whatnot. So with that being said, the next generation of these experiments are going to include some passive instrumentation, and so we can identify, temperature points, the tops and bottoms of the capsules. It's not as good as getting a temperature measurement on the fuel itself, but it's sometimes the best that you can do. Instrumented experiments with lead outs. So basically, having a thermocouple dropped into these becomes a much more complicated and expensive endeavor. And so that tends to kind of be reserved for, say, later or higher TRL tests. So a lot of these are being done to look at basic, qualitative comparisons to controls, post-irradiation furnace tests, transitions in the tree to kind of get, generic or general behavior, and justify, basically provide down selection for fuel design and justify future experiment expenses. I don't know if that makes sense or not, but
is there any plan on comparing? Well, I think it would be nice actually to compare one of those samples with a reference sample that is from the same type of fuel. Yes. With the same amount of burn up through conventional method. In terms of microstructure, to make sure that are those, because in the end that will be the validation of this entire program in my eyes. Are you getting to the same type of microstructures by this accelerated way?
I don't know yet. So I'll start off, and I know you mentioned microstructures, right? But the first step and the thing that's easiest or available for us to do is to do a lot of these modeling comparisons. Which is at least understanding some of the basic behaviors and expectations. So we've done a lot of this type of analysis, looking at being able to model and replicate, for example, just radial swelling or cladding strain on a EBR2 pin, and then being able to model that cladding strain in different increments, matching that cladding strain with what we'd expect to see in different fast experiments. And then in terms of PIE, these just came out of the reactor last summer. We've just finished, I'm in the middle of doing our internal review still on the paper for all of this work. So we just barely finished about 2 months ago, the NRAD and PGS data. So we haven't even gotten to destructive testing yet. Ideally, we might get to that this summer. To answer your questions directly now, we are We have microstructural analysis for various EBR2 fuel. We have microstructural analysis for all of our AFC experiments that we've done, and we fully plan on doing that same, comparable analysis for all of these. So yes.
Sounds good.
As well as other properties. I mean, there's some, it'll be exciting. Some of the other advancements we've made in that characterization includes, advances in being able to capture, local thermal conductivity as a function of various features through called the thermal conductivity microscope. It uses thermal reflectance methods to, capture very local thermal properties. You can use that to back out mechanical properties as well. So tensor components for modulus. And so all of these things, being able to couple those, explicit properties, which are really important for a lot of the models, to microstructural features is will be very important and interesting for sure.
How long do you need to keep them to cool them before you actually open those capsules?
So these so they came out of the reactor at the end of April in 2020. The shipment process, after analysis and everything, takes a couple of months. We had them unloaded from the cask in August, and we initiated the radiography in October. So that's 6 months. Now, those were for some lower burnup. I imagine there may be a longer period of time for some of the higher burnup ones, but they weren't too bad.
Right. I'm done with questions. If there's anybody else.
When someone's got anything, I mean, even if it's not about, I don't know, about this, it could be generic, basic. All right.
We have a question.
Oh, perfect.
So unfortunately, I came late because of class. I was wondering why they use HT9 over other metals. What is it?
Boone, did you hear that?
Kind of. Could you repeat it for me?
Can you be a little bit louder?
Can you tell? I guess
No, he could hear you from there. You just need to be louder.
Okay. Why do you use HT9 metals instead of another one? I guess.
Yeah. So HT9. So historically, I'll say 316. Well, some standard stainless steels were used. Stainless steels typically have a lot of nickel. And nickel's problematic for its capacity to capture neutrons and then decay and alpha decay and formation of helium. You still get a little bit of that with some HT9, but that's the biggest reason that's been used over 316. It's used over, conventionally we use zirconium, right, in LWRs. We don't do that for sodium fast reactors, in part because you don't need to, and stainless steel, I think, generally has some better mechanical properties than zirconium. And there's other alloys being looked at, but for the most part, HT9 has been the kind of historical baseline for it. It's probably not the most satisfying answer, but people have tried a lot of different alloys, a variety of grades, T91. I know the French explored with a variety of different alloys with the Phoenix reactors, but for the US, we use HT9.
Okay, thank you.
So
It
also has very low swelling properties. That's the other thing. So if you look at like swelling compared to DPA, sorry, it doesn't get into breakaway like swelling until a very high dose. And so for fuels that you're trying to get to like relatively high burnup, it tends to be very stable and safe.
Thank you.
Yeah.
Well, if there's no other questions, maybe we can thank Boone for his very nice presentation and for teaching us about fast reactor. I think it's a reactor we need to keep in mind for possible experiments in the future. Thank you.
So if anybody has any other questions, I don't know if you guys sent out the email, but both Jamel and Ben, so Dr. Kaomi and Dr. Beeler have my contact information. Feel free to reach out. So
Sounds good.
thank you all.
Thank you.
Thanks.
Thank you.